Hi all, and I welcome you again to my YouTube channel Math Universe with Dr. Naseer Ahmed. Now, today we are going to start with a chapter Continuity and Differentiability. Now, coming to this chapter, as you are aware, it's a bit big chapter. And in first exercise, continuity 5.1 problems we have, and remaining 5.2 to 5.7 is only on differentiation. So what I have planned here, I am going to make this one into two videos. First video will confine with continuity concept in detail along with the problem of model question paper. After that, I am going to take differentiability, nothing but under what condition a function is differentiable or not differentiable. So after I complete this, I will be going for part 2, where I am going to talk about all the different ways of method of differentiation. Okay, I would like to say method of differentiation. Okay, so with this, let us start with continuity now. So continuity, when do we say a function is continuous? Let us first understand this. Geometrically, a function y is equal to f of x is said to be continuous if I am able to draw the graph without lifting the hand. For example, if you see some of the example, if we see a polynomial function y equal to x square, what is the graph of this? This is a parabola, and I can just draw the graph like this. You can just see touching at 0, and then this is the example of a function to be continuous. First, let us understand geometrically. I also know some students will be having an argument, sir, actually this is not continuous. How come? The argument from the student end will be, sir, when you have drawn the x-axis and y-axis, you rose the hand. Try to understand, my dear student. Surely I am going to raise my hand when I am going to draw x-axis as well as what? Y-axis, because I have to have frame of reference. Correct? No? Whatever we are talking about, or whatever position, if, for example, we are in one particular place, frame of reference. From there you are going to start. Correct? No? So first I want coordinate axis, then the diagram. Okay? So this is the example of continuous function. Similarly, let us try to take some other y equal to x cube. The graph of this, as we are aware, it is this. Again, it's a continuous function. Coming to some other example, let us suppose trigonometric function. Before I just go ahead, just I want to comment here. One more I will take, y equal to x, our identity function. And this graph, as we know, this graph is a line passing to the origin. This is the graph. Now, I just want to give one comment from here. What? From here, what I want to comment is, every polynomial function is continuous. Every polynomial function is continuous. See, definition of polynomial first. We will also define analytically first with respect to geometry. So what is polynomial function? Any function of this form, a0 plus a1x plus a2x square plus a3x cube moves on an x power n, where the power, you can see, no, x power n here, then power is 3, 2, and here 1. I can say that here there is no x term. I can say this x power 0. So the power is always a whole number, or I can say it is non-negative integer. Integer and positive integer and 0. So that's what I said, non-negative integer. And this a0, a1, a2, a3 up to an, all these are real numbers. And if at all I'm saying this is a polynomial of degree n, it's multiple. What's the degree? What's the degree here? X power. What's the power of x? N. What is multiple? An. That should also be not equal to 0. Only then we say that it is a polynomial of degree n. Let's spend some time here. When I'm saying a is when I equal to 0, a0 when I equal to 1, a1 when I equal to 2, a2 then a3 up to an. All these are what? Real numbers. And this n is a whole number. So we have to make sure when we are deciding a polynomial, this criteria should be satisfied. What are the criteria? First of all, for any polynomial of degree n, its coefficient. This we call coefficient n. A3, A2, multiple of variable. A constant multiple of a variable we call coefficient. Whereas here, since x is not there here actually, because x power is 1, this we call constant. Okay. Now I just introduce this term so that you understand why n is a whole number. I can say this is x power 0. Okay. Now, when I'm talking about polynomial, this criteria should be satisfied that power is always a whole number and the multiples can be any real number. Now just see here. This one, degree is 2. Since highest degree is 2, this is what? Quadratic. This is a quadratic polynomial. Quadratic polynomial. And here if you see, highest degree is 3, multiple is 1. Here also multiple is 1, but higher degree is 3. So this is cubic polynomial. And for that, we have got the graph. And here it's a linear polynomial. And to be specific, it's an identity function. With respect to function, it is what? Identity function, to be very specific. So, what have we understood here? That this all are obeying this condition, hence it's continuous. So, from here, what I want to comment, one most important, and this all are important for our 1-marker question. As you know, we are getting 1-marker question from this chapter also, both on continuity and differentiability. So, I can just give a note here, what? Every polynomial function is continuous. And one question will come, sir, continuous where? Continuous for all x belong to real number. For each and every real number. You can see it is starting from here, no? Very least value to the highest value. For all this x value, graph is present and it's continuous. Here also same thing. Okay, same thing here. Next, let us try to also understand for modulus function also. First, you make a note of this. Okay, let us continue as we are discussing continuous function. See, whatever we are going to discuss is only for function. Okay. Now let us move on to modulus function. So see carefully the graph of mod. If I take y equal to f of x equal to mod x, as usual, we write y in terms of x. So the graph of mod function, recall, just a V-shaped graph. Okay, and this point is 0, 0. As you can see, both x and y is 0. Now the question is how to know, no? So see, it is coming down, that is decreasing we call, and here increasing. That I will discuss in detail when I take increasing decreasing function. Okay. Now when we are talking this, how to know, no? This point, at this point is turning. Very simple. Come to modulus. Under the modulus, whatever is there, equal to 0, you'll get x equal to 0. So you'll get the point at which the function is changing its behavior. Turning point we call. First it is decreasing and then it is increasing. Okay, coming down and then going up. Now, as you can see, we were able to draw without lifting the hand. Now it is, we have been confined with this graph only usually, but let us take this also, some other, if you have some number. Now how to draw the graph? Very simple. You know that mod will give always V shape. Now this, whatever is there under the mod, now it's just going to shift the, this we call, let us use the word kink point. This we call kink point. Sharp bend is, we call kink. Okay, so here, how to get the kink? Very simple. The term inside the modular, that is this term, equal to 0. So x plus 6 is equal to 0, or x is equal to minus 6. So the same graph which is there at 0, x equal to 0, should be present where now? X equal to minus 6, nothing but here, negative part of x-axis. So let's draw that. So minus 6 somewhere here. Now if I draw, see carefully. Purposefully I am making sure drawing one side to make you and have a feel that it is continuous function. Sir, what about if I have some positive? Very simple. Let us suppose I'll take some, say I'll take the same number itself. Now, the term inside the modulus, that is x minus 6, equal to 0. If I equate to 0, x minus 6 to 0, I will get x is equal to plus 6. So nothing but I am going to have that sharp bend where at x is equal to 6. So try to draw the graph. So 6, search for 6, it will be right of origin. Now again complete the graph and then move on. And this all graphs are also required for us in as and how we go for the next set of chapter. Don't think of next chapter also. Present chapter, in this chapter, differentiability, no, I'm going to discuss one point here. Okay. But let I first complete what? Continuous. Okay. Fine. So this will be the way you are going to draw the graph. So very simple. Whenever you have got modulus function, the term inside the mod equal to 0, you are going to get a point, x value. Thus, this point is going to decide how my function is behaving. So it is decreasing and then increasing. So every modulus function is what? Continuous function. So what about this graph, sir? See, one more thing, no? Understand. If you know primary graph, no, you can go for remaining. Since I understood primary graph, or I can say parent graph, or these are hybrids. Okay, now let's see this. How are you going to deal with this? Very simple. Go to this. Here, there's no sign means positive. So the outcome should be always non-negative. Correct, now? But here, this entire outcome, which one? The mod x, whichever is there, no, this one is what? Non-negative. I have multiplied with the minus sign. So the entire output, nothing but minus mod of x. Mod of x is non-negative, but minus of this will be what? Whenever we multiply negative, inequality will change. So I have got this. How it will change? Simple, I'll just say. See, for example, 3 is less than 5. Do you agree? Multiply by negative. If I multiply by minus 1, see, minus 1 into 3, then minus 1 into 5. What is minus 1 into 3? Minus 3, and this is minus 5. Now, minus 3 is larger than minus 5. So whenever you multiply or divide by a negative term, inequality will reverse. I use the word reverse. It means less will change to greater than here, and greater than will change to less than. Similarly, less or equal to will change to greater or equal to, and greater or equal to will change to less or equal to. Thus, it will get reverse. Now, you just see the graph which I have got here. The same graph I can have here. Okay, much better. So y equal to minus of mod x. Very simple. Whatever the graph was there above, no, it was non-negative, so it is above x-axis. Now it's coming down. We are going to pull it down. So when I'm going to pull it down, the graph will be like this. Yes, and then down. This is again continuous function. Let us suppose we have y is equal to minus of x minus 7. Very simple. This is the parent graph now. This all or no? We are going to go with this. So the term inside this equal to 0, x is equal to 7. So draw the graph. 7 is somewhere here. Right? So my mod graph will be going to be like this. Okay. Similarly, let us suppose that I want what? y is equal to minus of x plus 7. That time inside the mod equal to 0, I'll get x is equal to minus 7. So take the graph equal to, and I have taken equal to 0 the term inside the mod. I got minus 7 and it will be somewhere here. And since already we know we have minus sign, so my graph will be like this. A chotu graph will take. So every modulus function is also continuous. Let us make a note here. What have we understood? Okay, that every modulus function is continuous for all x belongs to real number. Okay, so I thought first I will go with the graphical approach to make you understand. Now let us try to understand analytically. Okay, make a note. Dear students, now having understood geometrically when do we say a function is continuous, that if you are able to draw the graph without lifting the hand, it's known as continuous function. Now let us try to understand analytically. Reason, sir, when we know graph, why not? See, for each and every problem we may not be able to draw the graph, so analytical approach is very important. Now listen carefully. Just let us have one figure, a diagram, so that things are very clear to you. Some diagrams will take. Now see this graph, and this graph I am taking the equation as y equal to f of x, and we are dealing with real valued function. When I say real valued function, as I have it here, f is a function from a to b. When I say real valued function, my codomain should be subset or equal to set of real number, and when I say real function, a should be subset or equal to a real number. So in short, when I say real valued function, domain and codomain are set of real numbers or subset of real numbers. We mean to say that we don't have any space for complex numbers. Okay, no space for complex numbers. Now, and it should be defined number, nothing but denominator should not be 0. Now you see carefully this. I have got a function, and whatever we are discussing, continuity, differentiability, we are discussing for function. Now let us say that I have got one point a here. I want to check the continuity of the function y equal to f of x at the point x is equal to a. But and here most important, the point which we are talking is on x-axis. Okay. Now in how many ways can I approach this point A? See carefully. See, since this point is lying on x-axis, yeah, I have got an x-axis here, and I can approach A only in two ways. Which are those? One is left of A, other is right of A. You see the arrow mark? I'm going near to A. Near to A. Now, when I'm going to approach near to A from the left, you see carefully. When I'm here, when we are here, corresponding value on the graph is here. When we are here, again the corresponding value is here. When I'm again here, I am approaching. As I know, I'm going near to A. I am also going near to. As I know, I am going near to A. I am also going to some value on the graph. Again, you see here. Again here. Again, I am here. Again, you are here. And ultimately, when I am very, very, very near to A, I am also very near to. And let us suppose that this value I will take as some f of A. How, sir? Alright, x equal to A, I want to evaluate. So wherever x is there, put x as A. What you will get? F of A. So value of y is what? F of A. Function value. This we call function value. What is function value? I want you to have a difference. Function value is that value which is obtained by substituting the required x value. Whatever the x value is there, substitute there, you will get corresponding y value. This we call function value. Just you are substituting and getting the answer. Whereas when I'm here, the way I have went left from the left to here, this we call limit value. I am approaching to a point. I am approaching to a point, and this we called left hand limit. In short, henceforth I will be writing LHL, and it is LIM f of x as x tends to a with a minus here. Now I want to spend some time here. What is a? Any real number. What I'm saying is whatever I'm defining here, it can be in negative part of x-axis also, it can be at 0, the origin also. Okay. Now, what's the significance of this minus? This minus is not talking whether a is positive, negative or 0. No. It's only talking that we are approaching to a from left of a. A is there, left of a, that we call left hand limit, in short LHL, and x tends to a minus. How to read this? Don't write LIM. Limit of f of x as x tends to a minus. Okay, and in this case, when I'm going, you can see here, and I'm approaching to which value? See, f of a. So in this case, it is f of a only, left hand limit. Whereas, see carefully, when I'm here, corresponding values are here. Again, I'm here for this. Again, for this, I'm here. Again, when we have, again we are here. Again, for this, we are here. Again, for this, we are here. Again, for this, we are here. So, approaching a from the right, we call right hand limit. What we call? Right hand limit. In short, we are going to write it to be RHL. LIM of f of x as x tends to, I am approaching from right of a, so a plus. Okay, so a plus means I am approaching the point a from right of a, but I am having minus left of a. That's what you can see very clearly. And again, you can see when I am approaching here, I am again having a function value itself. First, let you understand this. First, is the graph continuous? Don't see this. Graphically, is it continuous? So see, yes, I am able to draw without raising the hand. And now you come here. If you see, left hand limit exists, nothing but it's a real number. Right hand limit exists, nothing but it's a real number. And both are equal, f of a, f of a. So when do we say limit exists? Limit exists provided left hand limit exists, right hand limit exists, and both are equal. And left hand limit and right hand limit both are equal to which number? Function value here. And not only that they are equal, they are also equal to a function value. Only then we say a function is continuous. Let us write in elaborate way. A function is said to be continuous at a point x is equal to a if limit of f of x as x tends to a minus, that is left hand limit, is equal to limit of f of x as x tends to a plus. This both should be equal to function value. Obviously, both left hand limit and right hand limit should exist. What I mean to say, the number should be a real number. Let us suppose I got undefined value infinity and mine here also infinity. You cannot say they are equal. When you want to compare, it should be a finite quantity. Okay. So let's write again above that left hand limit is equal to right hand limit is equal to function value. Okay. Only then we say function is continuous. Now, I have seen many times students, they will not give importance for function value. As soon limit value exists, no, student think it is continuous. Let us have a talk on this with respect to the diagram. So this is the way we are going to talk about function is continuous or not. And one more thing. In place of writing like this, as soon left hand limit exists, right hand limit exists, we also write this one as limit of f of x as x tends to a is equal to the function value. Now try to understand what is the significance of this left hand side. Whenever I write like this, it means both this left hand limit exists, right hand limit exists, both are equal. So in place of writing this, we always write this, provided left hand limit exists, right hand limit exists, and both are equal. It also means that as soon as you see limit exist, as soon as they say limit exists, what should click? Left hand limit exists, right hand limit exists. Not only that, they are equal also. Okay. Now, first make a note of this. We will have a talk with respect to left hand limit, right hand limit as well. Make a note. Okay, dear students, I have written this one as it is to make you understand that if the limit value is not equal to function value, we are thinking, sometimes students are thinking that then also is continuous. So let us take a diagram for this, okay? A general diagram, okay? See this carefully. Let us use blue color. See this. I have just drawn one diagram, an open ball here, and there's one diagram, okay? See, at this particular point on x-axis, the point is again, okay, yeah, we'll take here only. And this graph is y equal to f of x. Now see carefully. I want to again check, and here, let us suppose I'm going to shade here. This is my function value, that is f of a. At this particular point, I have got function value. Now just see, let us try to draw the graph again. Okay, see, I am drawing the graph. At A, this is also a part of the graph. I have to lift my hand, shade this, again lift the hand, and then complete the graph. I repeat, first start drawing, then before going to A, take the hand, shade it, again take the hand, and then complete the graph. So I am not able to draw this graph without lifting the hand. So graphically, it is discontinuous. What is discontinuous? A point at which the function is not continuous. Nothing but I am raising my hand at that point. Now let's see. I draw, tuck, 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 and here raising the hand and then drawing. So discontinuous at which point? X is equal to A. Okay, at x is equal to A, it is discontinuous. Graphically we know. Now let us try to analyze analytically also. Now, A, I can approach from the left, and when I am here, corresponding elements are here. Again when I am here, again here, again here, yes I am here, again here, yes I am here, and when I am here, again here. So this, I am approaching this number, correct? No, that number on y axis, let us suppose that it is some value L1, or just L I'll take, okay, just L. So what is my left hand limit? Limit of f of x as x tends to a minus is equal to L. And L is a real number. One question will come, sir, how can you say? I have marked on which axis? Y axis. Only real numbers will be there on x and y axis. Simple. Okay, left hand limit I got. Now come to right hand limit. Right hand limit. See carefully. When I am here, okay, I am again here, and I want to use one word, neighborhood here. Neighborhood means what? Very, 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 very close to the point. So here, this is my neighborhood, very, very close. Baju wala. Neighborhood. Very, very, very close to the point. I am nowhere far from the point. Okay. So again, when I am here, yeah, corresponding point. Again when I am here, again yes here. Again when I am here, it is this side. Again here, this. Again here, yes I am here. Again for this, corresponding values here. Again when I am going near to A, I am here. So I'm, see, near to A, I am just approaching this point, and that point is what? L. So right hand limit of f of x as x tends to A plus is what? L again. That is what? Real number. This is also a real number. Now you see, L, yeah, both are same number. So here, left hand limit is equal to right hand limit. First they exist and they are equal. So I can say left hand limit is equal to right hand limit, or this also implies limit of f of x as x tends to A minus is equal to limit of f of x as x tends to A plus. But is this equal to function value? See, this is whatever we have approached is limit value. This I call limit value. Okay, we call limit value, and this is the function value. So this is equal to what? L, which is not equal to the function value. Understand this. This time limit value exists. Both left hand limit exists, right hand limit exists. Both are equal to each other, but not equal to function value. So whenever limit value exist but not equal to function value, then also the graph is discontinuous. Whereas as soon as the graph is continuous, it should be also equal to function value. Majority of the time student will ignore this. I don't want you to do this error. And again, this, since it exists, I can combine this together. I can write limit of f of x as x tends to a is not equal to the function value. Okay, I hope this is clear. Okay, so first primary thing is limit value should exist. I'm just thinking, let I make you understand one more point. Okay, first make a note of this. I want to okay, let us say that is first graph, this is your second graph. Now I'm going to just edit in this only. Have you made a note? Okay, now see carefully. I am removing this point. Now what can we talk about? Continuity. See carefully. Tuck, I'll draw the graph. At A, there is no graph. Open, this is what we call open ball, means value not taken. Value, open ball means value not taken. Closed ball means value taken. Write it here. Open ball means value not taken. Value not taken. Okay. Now, value is not taken. Fine. Understood. So just see, draw, raise the hand where at A and again continue. So A is a point of discontinuity still, even when function value is not defined. So what's the meaning here? What I want to convey? Let us suppose you got limit value but function value not given. Now what's happening? Function value not given. Then also it is discontinuous value. And that point is on x-axis. Okay? Dear students, let us try to understand one more concept, that just now when we discuss about continuous, first problem example means, I mean to say the general graph which I took, limit value was equal to function value. Second one was limit value not equal to function value, due to which second graph was discontinuous. First one was continuous. Now the question comes, why is that limit value should exist? Can it happen that limit value does not exist? Then also, I repeat, limit value does not exist. If this is the criteria, whether it is going to affect continuity. Let us try to have a talk on that. So third graph, see carefully. General graph I'm taking, nowhere a particular graph. Just understand this concept. Then you see for one marker how easily you can answer. And for differentiability also, no, we are going to use this logic only. Okay, come on, pay attention. See this one graph, and then so okay, it is here. Oh, okay, fine. So at the point x is equal to a, always the point which we are discussing about continuity or not, discontinuous or continuous, is on x-axis. Don't forget that. It's on domain. It's on domain. So always our point, let's have a note here, point of discussion is in domain. Correct? No? Whereas whatever the limit value and function value you are getting, that is on codomain, I can say. Let's have that. What? Limit value and function value. Limit value, when I say, that is, let us suppose L, we are talking about whatever we spoke in the last problem, and function value is f of a. Both are in codomain. The point of discussion, that is, for example, at, when I say x is equal to a, this a is where? In domain. Okay, that's why it's an x-axis for the point at which we are discussing, and limit value and function value is on y-axis. Now see, I'll just give an open ball here. Why open ball is given here? Because if I won't give open ball, for A, we have this also a function value and this also a value. It's not a function because it should not have more than one point of intersection for the vertical line. Correct? Now let us have a vertical line here. At x is equal to A. Okay, A is here. And on this detailedly I have explained in inverse trigonometric functions. Okay, kindly go to that vertical line test and horizontal line test. It's a function. Wherever you draw vertical line, it's only one point of intersection. Now you see carefully, this is the graph y equal to f of x. Now this is a continuous function. See, I will draw the graph. After this, at A, I have to raise the hand and then come to the graph. Therefore, A is point of discontinuity. A is point of discontinuity. Fine. Now, mathematically, how to know? So, first let us suppose this value is some, okay, and here also some value we are having, okay. Now see carefully. Coming to the left hand limit, LIM of f of x as x tends to a. When I am left of a, see here, when I am here, my corresponding value is here. When I'm here, corresponding curve value is here. When I'm here, again I'm here. When I'm here, again it is here. When I'm here, again it is here. Again when I'm here, here. So I'm approaching this value. As when I'm approaching near to A, I'm approaching this value, and this I will say some L1. Limit value L1. So left hand limit value is L1. Then let us talk about right hand limit. Now you see carefully. As and how I am approaching right of A. So see here, then corresponding one here. When I'm here, again I'm here. When I'm here, yes, when I'm still approaching near to A, and here. Again here, yes, here. Again very near to A, again here. And this I'm approaching, see, value is not defined. Yes, function value is not defined at A, at this. But I'm approaching to a number very close to this, and that number, let us say here, is L2. This is L2. So the right hand limit is LIM f of x as x tends to a plus is L2. L2 is a real number. L1 is also a real number. So how can you say that? Array, it is lying on y-axis. I have marked them. So it is one of the real number, definitely. But see the graph. I have not taken purposefully a particular value on y-axis, not here also. And I want you to analyze from here only. Are these two values same? You see, there's a difference. There's a gap between them. And as and how we climb up on y-axis, value of y will increase or decrease. Think. Value of y will increase or decrease. If I have got 1 here, then here it will be more than 1. More than 1. So the value is increasing. So surely one thing is very clear. What? It is clear that from the graph, L1 and L2 both are unequal. But what is L1? Left hand limit. And what about L2? Right hand limit. And limit does not exist. So far, first and second, I took an example where limit exists. Okay. But here, I take an example where limit does not exist and is discontinuous. It is discontinuous. So, when limit doesn't exist, you can see the graph is surely not going to be continuous. So, if limit does not exist, straight away we can comment it is discontinuous. Okay. So, here, limit of f of x as x tends to a does not exist. Make a note of this. Okay, so limit does not exist. So from here we can say that limit does not exist implies f of x is what? Discontinuous function. Okay. Make a note of this. Okay. Yes, dear students, having understood that if limit does not exist, it's a discontinuous function. But here, the last one we took, left hand limit, right hand limit, both exist. What if they won't exist. Let us take this one last two cases, okay? 1, 2, 3, I think this is the fourth one. See the graph again. Best way to understand these things are by graph. See carefully. Then in no time you can complete the problems. See, I have got a graph, but this time the graph is moving up, 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 up. So I have given dotted line. Dotted line means at this particular value, at this particular point, the value is not defined. And let us suppose that I have here value is not taken, but here value is taken, okay? And it's just moving to up to like this, it moves on to infinity. So here, as you can see, that again is a function y equal to f of x. You can draw a vertical line, only one point of intersection. And as in how you are moving towards the left, the graph is going here, again left, from left of here, graph is going up, again up, again up. It just moves up, 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 up to where? Plus infinity. And you don't forget this side you have got minus infinity. See, when I say plus infinity, minus infinity, those are not numbers. It's a notation saying that right of 0, the values are positive, increase as a huge quantity towards the right, and here we have least quantity towards the left of 0. Similarly, above 0, a huge quantity, because here all are positive. So later on it will be a huge quantity, and here very less quantity. So here when I talk about the limit value, first of all, is it continuous? Just see, I'm drawing it, raising the hand, and again drawing it. So it's a discontinuous A. So we are talking about continuity. I'll show you about a function only, okay? So limit of f of x as x tends to a minus, if I talk about left hand limit, and you can see the left hand limit is undefined, it's going to plus infinity, and this is not a real number. When I say real number, it's open interval minus infinity to plus infinity. Don't forget, both plus or minus infinity does not belong to R. R is in fact open interval minus infinity to plus infinity, okay? Coming to right hand limit. Limit of f of x as x tends to a plus, nothing but I am coming right of a. So when I am here, I am corresponding element here. Next, when I am here, again I am here. When I am here, again I am coming near to this. Again, see this. It is attaining a value, and that value, let us suppose some value L. Okay, L1 let it be. And it's a real number because it's been plotted on y-axis. So here, one more thing what you can see is, here limit doesn't exist. Why? Left hand limit is not a real number. And one more thing here. Purposefully I found right hand limit to make you understand. In calculating the limit, if one of the limit doesn't exist, no need to calculate the other limit. I mean to say, let us suppose you have found left hand limit and it doesn't exist. No need to waste your time to find right hand limit, because ultimately for a function to be continuous, limit should exist and it should be equal to function value. That was the main motive of me taking this diagram there. So same thing we can talk about right hand limit. First let's comment here. And here we are least bothered to talk about function value also, because the limit doesn't exist. Whether it's equal to whether we find function value or not, okay, doesn't have any for us any advantage there. So I can just say, but anyway, if at all you want function value, here in this case is both same. Function value and right hand limit both are same. Did you have this? Yeah, here my limit value and function value are same. Left, I mean right hand limit. Then also no very useful. So therefore, f of x is discontinuous at x is equal to a. Now the last one, what if I have right hand limit doesn't exist? Same, no change. Let's have a diagram a bit faster. So let us suppose that we have one function like this, and one function going like this only. But here there is a difference. What? At this point A, okay, let us take a bit more right. Okay, when I'm drawing this vertical line, this is never taking, but here it has attained the value. Okay. Now let us just extend this still more. Okay, it's just approaching but never meeting. and if it meets, it will not be a function. Okay, first of all. Okay, fine. So here my main motive here to make you understand is when you talk about the limit here again. See, as and I'm going to the right, left, from the left of A. At this point, I'm here on the graph. Again, I go here. I'm again here on the graph. Again here. Again here. When I'm here, again I'm down. And when I'm near to A, it's this value. I suppose this value is some L1. So my left hand limit is limit of f of x as x tends to A minus is equal to L1. And this L1 again is a function value. I just want to make this clear that even if it is function value, one of the limit is equal to function value, then also nowhere useful to talk about continuity. Okay. Next, moving on to right hand limit f of x as x tends to A plus. It just moved to minus infinity, which is not a real number, which implies f of x is discontinuous. Continuous at x is equal to A, as limit does not exist. As limit does not exist. So whenever limit does not exist, we can always comment the function is discontinuous. So f of is discontinuous. Again here also, as limit does not exist. D any mention does not exist. Okay, fine. So with this, now let us move on to a small concept and then the problems. Okay, make a note of this. Students, having understood all the basic things, now let us try to list out all those functions which are continuous and also discontinuous, and then we'll have the problems. Okay, so list of continuous function. First one, polynomial function. Okay, here whatever the function I'm talking about, I'm talking with respect to the real number r. So polynomial function are continuous. Examples can be y equal to x square plus x minus 7, okay, under the root, and I can have half also here. Power should be always a whole number for x. The multiple can be any real numbers, right? One more example, if you have x power 3 minus 7. Next, a constant function. Every constant function is continuous, which is, for example, y is equal to, general C, where C is any real number. So in particular, y is equal to minus 7. As soon as you see the minus 7, at the minus 7 you have to draw a line parallel to x-axis, and this is an example of what? Continuous function. Like this you can have so many. Okay, next is modulus function. As we discussed in detail, every modulus function is what? Continuous. Okay, so y is equal to mod x, y is equal to mod x plus 8, and so on. Next, coming to trigonometric function, y equal to sin x, y equal to cos x are continuous in R, the entire real number R. Now, having understood this, let us also try to understand first the definition again, and then we will try to take some algebra of continuous function there. So now here, let us move ahead. So definition for a function to be continuous. As we just understood, for a function to be continuous, limit value should be equal to function value. When I say limit value, it means left hand limit should be equal to right hand limit, and it should be equal to function value. This we call left hand limit, this we call right hand limit, and this is our function value. Function value are those where we are going to just obtain the value as soon we substitute. Okay. Now, if it is not satisfying, this is first point as a note. See, when I say discontinuous, it means this should not be obeyed. So limit value should not be equal to function value. When I say limit value should not be equal to function value, it can happen that left hand limit, right hand limit exist but not equal to function value, or it can happen that left hand limit exists, right hand limit exists but both are unequal. Okay, or it can happen that left hand limit or right hand limit doesn't exist, or both doesn't exist. All the cases are there. So this will be discontinuous at x is equal to a. Now this is at a point. Now how are we going to discuss the interval in the closed interval a comma b? When I want to discuss in the closed interval a comma b, I want to talk about continuity. Then how we are going to go ahead? We are going to take one general point. See, we cannot take each and every point here. Okay, we have got infinitely many points between two real numbers. So what we are going to do is we'll try to take one point, let us suppose C, and in the open interval a comma b, any point. So, and then we are going to take the limit value, and we are going to find for that point C and function value. Both should be same. Okay, this is for any point in between. Now, if I just talk about the number line, see this carefully. A is here, B is here, and the point C anywhere. And I've taken open interval. After we finish that, what we are going to do is at the end points, that is A and B, for end point A, you see carefully, for A, we can approach A only from the left or right, only right of A. We cannot approach left of A because there is no number line here, correct? No. So for at the end points, that is at A, we are only going to find the left hand limit, I mean to say right hand limit, only going to find right hand limit, and that should be equal to function value. Only in that case it is continuous at x is equal to a. Similarly, point C, at B I can approach only from the left of B, nothing but left hand limit. So left hand limit should be equal to function value. So limit of f of x as x tends to b will be equal to f of b minus, sorry, f of b and here minus. Okay, the function value at b should be equal to left hand limit of the function f of x. Limit, I repeat, function value should be equal to left hand limit at b, because from the right we cannot come. This is for the interval case. Okay, dear students, now let us take algebra of functions. See, so far we have discussed only one function at a time. Okay, so let us suppose we have got more than one function. That's what we call algebra. No, the same thing in school is no. After learning 1, 2, 3, you started learning addition, subtraction, multiplication, division, nothing but algebra of numbers. So here, algebra for a while. Algebra of continuous function. So the heading as it suggests, no, first it should be a continuous function, and we have got, let's suppose if we have two functions, that is f of x and g of x. F of x and g of x are two continuous function at, let us suppose, x equal to c. They are continuous. Then what is going to happen? First point, addition as well as subtraction. Okay, let us club all. Okay, C I have taken, so C here. Let us take all at once. Sum or difference. Okay, and difference. Then product of those two are the same point. Okay, C, no, C I have taken here. Okay, C. Since I have taken C, so it will be C. Similarly, scalar also. One means I have a number multiplied to a function. Okay, special case of this. Here both are function, but here it is scalar multiplication and the function are also continuous. Are also continuous. At x equal to c. Whereas coming to division, no, f of a by g of a, we have to be sure that g of a is not equal to 0. Only then we are going to say it is what? The continuous. If g of a, the denominator is not equal to 0, then it is continuous. So having understood this concept, no, this continuous at x equal to c. This also brings to one important we can have one new logic. What if I have got two function or more than two function continuous at the point x equal to c, then some difference product and scalar multiplication is also continuous. Coming to division, denominator should not be equal to 0, only then it will be continuous. Or okay, again I have taken c here, so I have c, it should be here. Maybe now we are discussing at a no, so it is always here there, but it can be any alphabet can be used, and c is any real number. Okay, c is any real number. Okay, mind it. Now having this logic, now what we can have is sum of the function. Now we can think of clubbing. Now all this will be now easy one marker question. See carefully. First, with this we can also think about now rational function. What are rational function? Any function of the form f of x is equal to p of x divided by q of x, where q of x is not equal to 0, and here both p of x and q of x are polynomials. Already defined polynomials already. So here the example of this can be, if I have got 1 divided by x minus 5, whether it's continuous or not. Now this is a polynomial degree 0. This is linear polynomial, therefore it's a rational function. It is continuous with respect to this logic, provided denominator is not equal to 0. X minus 5 denominator should not be equal to 0, or x should not be equal to 5. So is continuous where for all x belongs to R but excluding 5. So we can also have one marker question for which point it is discontinuous, x equal to 5, because we get undefined. Okay, function is not defined. 5 minus 5 is what? 5 minus 5 is what? 0. 1 by 0 is what? Undefined. Now coming to trigonometry, all the remaining other 4 trigonometric functions, sine and cos, is already continuous for in R. Now coming to other trigonometric function, before we go ahead, one note we let us take here, that when is actually sine and cos are 0. Sine x is 0 whenever x is integral multiple of pi, whereas cos x is 0 whenever x is odd multiple of pi by 2, where n is an integer. Okay, so with this, tan x is what? Sin x by cos x. Correct? So cos should not be equal to 0. Nothing but, see, cos to be 0, x should be not an odd multiple of pi by 2. Now here cos should not be equal to 0. Correct? So it means x should not be odd multiple of pi by 2. See, always I have a habit of writing plus or minus here. 2n plus 1 or 2n minus 1. Any one will become exam, not both. But student, no. If I use 2n minus 1, they'll forget that 2n plus 1 is also odd. Okay, so I just always have a habit as a precaution. This is continuous whenever it is not equal to, x is not equal to this. Similarly, cot is what? Cos by sine. So sine should not be 0. So when sine x not equal to 0? Sine x is 0 for x is equal to integral multiple of pi. So x should not be equal to integral multiple of pi, where n is what? Integer. Similarly, cosecant x. Cosecant x is what? 1 by sine x. And sine x should not be equal to 0. Same, x should not be. Actually, this is also defining the domain of all the 6 trigonometric function. Here it is true for all x belongs to R. When sine and cos is defined, I mean to say. Then secant x. What is secant x? 1 by cos x. And cos x should not be equal to 0, or x should not be an odd multiple of pi by 2 when n is integer. So mean to say all the 6 means sin and cos is continuous in R, but tan, cot, cosecant, secant are continuous in its domain. Domain is this. They should not attain this value, R minus this numbers, correct? So this implies tan x, cot x, cosecant x, and which one? Secant x are continuous in its domain. Okay, make a note. Okay, dear students, let us take some examples of some standard function which are discontinuous. Okay, so I will try to go with the first PUC important graph you had no with respect to this. Okay, so the first one in that, okay, example for, okay, examples of discontinuous function. Discontinuous functions. First can be sinum function or signum, whatever way we call, but spelling should be correct. Definition of this is f of x is equal to mod x by x where x is not equal to 0, z and 0 when x is equal to 0. Now when we simplify this, we are going to have, we know that mod x, we know that, let us recall this, mod x is plus x when x is positive, minus x when x is negative, 0 when x is 0. So here mod is there. So only here when x is not equal to 0, I've got two cases. See carefully. So when x is more than 0, x is less than 0, and x is equal to 0. For x equal to 0, we have got 0 only, no problem. Now denominator x. So x is positive. So mod x when x is positive, mod x is plus x. Then when x is negative, mod x is what? Minus x. Now simplify this. What are we going to get? Here very clearly x will get cancelled, right? I'll get 1 here. Again x will get cancelled. I'll get minus 1 here. So I just also derived now how we get the signum function. So see carefully. The signum function is plus 1 when x is positive, minus 1 when x is negative, 0 when x is equal to 0. Now when I plot the graph of this, as you know, that the graph goes like this, at minus 1, open ball, then here close, 0, then again open ball, then right. So just if I try to draw the graph, here I draw, I raise the hand. Now when I'm raising the hand, at which point am I raising the hand? Is it minus 1 or 0? Many students know when we go here, when we raise the hand, they'll see minus 1 and they'll think at minus 1 we have raised the hand. No, my dear student, this graph is the output for all the x value present here. So when I'm raising the hand, see carefully, origin coordinates are 0, 0. So I'm raising the hand for this 0, and then I'm shading here again. See, I'm drawing the graph till here for this x-axis value, graph is there. At this 0, I'm raising the hand, then I'm shading. Again for the same 0, I'm raising the hand, and then I'm completing this graph. So point of discontinuity is x equal to 0. Understand this. Not other than x is equal to 0. This 0, not minus 1 nor 1. Okay. Similarly, greatest integer function. Other one more example. See carefully. As we know, this is the symbol for greatest integer function. So when rectangle bracket is greatest integer function less or equal to x. Okay, greatest integer function. The numbers will be less or equal to x. So the graph of this goes like this. Okay, now let's between 0 to 1 the graph is this. If at all you want to know all this from basic, you can surely refer to the first PUC relation and functions. All the graph I have discussed there. Okay, now only I just want to talk about the concept. Okay, now see this, when I'm drawing the graph, see, I'm raising the hand. I'm raising the hand not for this minus 3, it is for x value minus 2. So I'm raising the hand at minus 2. Again draw the graph, raising at minus 1. Again draw the graph, raising the hand at 0. Again draw the graph, raising the hand at which one? 1. Again draw the graph, raising the hand at 2. Again I'm going to draw the graph, raise the hand at 3. So it is discontinuous for all x belongs to integer. Or we can also have one question now, for which point is continuous. So I can also say that it is continuous for all x belongs to R except 0. Here also I can say it is continuous for all x belongs to real number other than integer. Okay, so so we have completed all the things, including the example for what discontinuous. We can also say no, one more such example is a rational function. If you remember this graph we had, no, just one short graph I will take. We had y is equal to 1 by x. This is also a very good example for discontinuous function. How was the graph of this? The graph was this. Okay, so this is discontinuous. X should not be equal to 0. Discontinuous at x equal to 0, because at x equal to 0 I'll get 1 by 0 nothing but undefined. Okay, so now let us take the problems. Make a note of this. Fine, dear students, let us move on to the problems on continuity, which is our 4 marks. 1 marker in the choices, I mean say an option of 1 marker, there is a question on differentiability also. So first I will complete continuity problem, all the 3, then I will discuss differentiability concept, and then we'll finish all the 1 marker. Okay, now see this question says find the value of k. Where is k in the question? Yeah, here it is. So that the function f of x defined by this is a continuous function. Try to understand when this flower bracket is given. Whenever my function behave more than one manner on the real number r. Now here at 5 it is behaving differently, and they are saying it is continuous at x equal to 5. So then find the value of k. See, when I say 5 here on the number line, here all the number this side is more than 5. So for more than 5, my function is this. So here f of x is 3x minus 5. Coming to less than 5 or equal to 5, this is the function value. F of x value is this, and it is for this side. So it is f of x is equal to kx plus 1. Okay, now coming to the solution. Since in the question they have said f of x is continuous at x is equal to 5, so I can say that left hand limit, we call for left hand limit minus sign on the number, then right hand limit should be equal to function value. So coming to the left hand limit, less than 5, correct? Less than 5, f of x is kx plus 1. So limit of kx plus 1 as x is tending to 5. Then limit of 5 plus, right, more than 5, here 3x minus 5. Now this time we are not going to take function value, because if I take function value also, equality is here. I have the same function f of x kx plus 1 is already used here, and already we have got one equation, and having one unknown, easily we can solve. So we can avoid function value. So wherever x is there, replace by 5, x is tending to 5, so I'll get k times of 5 plus 1. Here they are saying wherever x is there, it is tending to which number? 5. Let us write it properly. So 3 times of 5 minus 5. what is the value? 5 into k is 5k plus 1 is equal to 3 5s are 15 minus 5. 15 minus 5 is how much? 15 minus 5 is 10. So 5k plus 1, if I transpose 1 the other side, 5k is equal to 10 minus 1, or I can say 5k is equal to 9. Cross multiply, k is equal to 9 divided by 5. Okay, so for this value, the function is continuous. It can also happen for 1 marker. It can be this question. You can just work out this part. And they can be for which value of k the function is discontinuous. It will be r minus 9 by 5. Okay. Now coming to this. Again, define the value of k if this function is continuous at x equal to 2. Since f of x is continuous at x is equal to 2, is it not limit value as x is tending to 2 minus left hand limit should be equal to right hand limit, and this should be equal to function value. So coming to left hand limit, so again at 2 it is behaving differently. Less than 2, f of x is kx square, and more than 2 f of x is 3. Okay, so less than 2 minus what? I am approaching from left of 2. Left of 2 means what? Less than 2. So wherever f of x is there, it is k times of x square as x is tending to 2. Then limit x is tending to 2 plus right of 2, f of x is 3. So wherever x, again no need of function value because at equal to 2, same function value which is used here will be coming into consideration. Anyway, we have got one equation, right? So wherever x is there, replaced by 2, nothing but x is tending to 2. So k times of 2 square. Wherever x is there, replaced by 2. So there is no x. 3 will remain 3. Try to understand. Since x was there, in place of x, it was replaced by r. X is approaching to 2, so 2 came here. Again, x is approaching to 2, but there is no x, so 3 remain 3. So k times of 2 square is 4 is equal to 3, or k is equal to 4. I mean to say k is equal to 3 by 4. So this will be the value for which the function will be continuous. Very easily we can finish the problems on continuity. For this all are for 4 marks. Okay, it's a 4 marker question, mind it. Okay, make a note of this, and this is from KSEAB model question paper problem 1 and 3. Make a note of this. Okay, dear students, let us move on to model question paper number 2, 4 marker question. Question says determine the value of k. K is here. If f of x is equal to k times of cos x divided by pi minus 2x is being given whenever x is not equal to pi by 2, and f of x is 3 when x is equal to pi by 2, is continuous at x equal to pi by 2. So if it is continuous at x equal to pi by 2, we have to find the value of k. So first, since f of x is continuous at x is equal to 2, is it not the limit value as x is tending to 2 minus should be equal to, okay, pi by 2, no, sorry, pi by 2 it is. Here also pi by 2. So limit of f of x as x tends to pi by 2 plus is equal to what? Function value. So limit value should be equal to function value. Now see carefully. When I have got here x is not equal to pi by 2, it means that on number line, whether I come from the left or the right, in both the cases what? It is not equal to pi by 2. It means what? In place of writing like this, I can write only limit of f of x as x tends to pi by 2, because Whether I'm coming from left of pi by 2 or right of pi by 2, both the times my function f of x is this only. Since I've got for left and right same, so there is no need to evaluate left hand limit, right hand limit separately. Okay, so that's what I wrote here. Now I'm going to write like this. Now let us go ahead. Now limit of f of x when x is not x is tending to pi by 2 is not equal to pi by 2. So not equal to pi by 2, f of x is k times of cos x divided by pi minus 2x, where x is tending to pi by 2. The function value at pi by 2. Function value at pi by 2 is 3. So substitute 3 here. Now apply the limit. Now see carefully, I'll just apply the limit and show you here. So apply the limit k as it is, then cos x is tending to pi by 2. So x is tending to pi by 2 here, then divided by pi minus 2 times of pi by 2. Right? Now k times of cos 90 is 0. 2 by 2 will get cancelled. Pi minus pi is 0. So answer is 0 by 0 form. 0 by 0 form. Now how to evaluate? Recall in first year PUC we had a result limit of sin x divided by x as x tends to 0 is 1, and this we call indeterminate form. Indeterminate form. Now we are going to evaluate this by using this result of first PUC. But for that I want what? Sin. What do we have? Cos. And here limit is for x, not for k. So k I can take out of the limit. Then limit of, here can't I write cos as sin of 90 minus x? Why we are doing so? To apply this result, numerator should be sin, not cosine. So we know sin of 90 minus x is cos x. Next, whatever angle is the same angle should be the denominator. So you see x multiple is minus 2, but here x multiple is minus 1. So if I take 2 common here, then what I will get? Pi by 2 minus x and is equal to 3 as it is. And x tending to pi by 2. See, one thing is very clear. If x is tending to pi by 2, the difference between x and pi by 2 will be 0, because they are going very, very close to each other. Or you can think as for rough transpose, which is actually not correct to say. Okay, as and how I am approaching, see this very carefully now. If I say this is x and this is pi by 2, there is some difference as and how I am approaching towards pi by 2. But as and how I am going very close to pi by 2, the difference between them will be very, very, very close to 0. I hope this is clear. So whether I write like this or I write x minus pi by 2 is tending to 0, both are same. Now see carefully k as it is. Now see carefully what I want to highlight. Okay, I'll do one thing. I'll go step by step. Half I will take out. Now see what's remaining? Limit sin of pi by 2 minus x divided by pi by 2 minus x, where x minus pi by 2 is tending to 0 is equal to 3. Now see carefully this entire value. This is going with this theorem. Result sin, yeah, sin. Whatever angle is there, same angle here, yeah, same angle. It should tend to 0, yeah, tending to 0. That is what? 1. So this entire value is what? 1. So k by 2 into 1 is equal to 3. Cross multiply, we can say k into 1 is k is equal to 2 into 3 is 6. So k equal to 6 will be the value for which this function will be continuous at x is equal to pi by 2. So with this all 4 mark are done. Now let us have the concept of differentiability. Okay, make a note of this. Now let us move on to differentiability. Now first let us understand what is the meaning of this. Why do we say a function is differentiable and sometimes we say it's not differentiable at a given point? What is the concept behind this? And the best way to understand is geometry. See here. Let us suppose that I have got one curve whose equation is y equal to f of x. Okay. Now, I'll take one point here. The point is x, and the corresponding y coordinate is here. So I put x is equal to x is back here. I'll get f of x here. Okay. Now, I'll take one more point here. The distance from here to here is h. Actually, it's very small, but for you to have a visualization, I've taken a bit far. Okay. So here it is x plus h. I want a corresponding. Show you how to get corresponding y value in this equation. Wherever x is there, put as x plus h. Then this will give us f of x plus h. Now, to this point, let us suppose this point is P and this point is what? Q. Let us try to join them. When I join these 2 points, P, Q, see carefully. We have a chord. Now, listen carefully. What now we want to do is fix any one of the point. Okay, fix any one of the point, and the line need not be just here. It can be, just move ahead, chord, or you can say secant, whatever. Now, fix any one of the point. Let us the point P is fixed. Now I'm going to walk along the curve and I'm going to come nearer to P. So when I'm doing so, before we go ahead, just see carefully. This coordinate P, the coordinate of P is x comma f of x. And the coordinate of Q is x plus h and f of x plus h. So here I can say name them as x1, y1, and this is x2, y2. Now, derivative, nothing but rate of change of quantity. Rate of change. So change in the y coordinate with the limit. Y coordinate is here f of x plus h, and here is f of x. So f of x plus h minus f of x divided by change in x coordinate. X plus h minus x. And this difference is very small. And if you very clearly observe, what is the formula to find slope of a line? M is equal to y2 minus y1 divided by x2 minus x1. So y2 minus y1, f of x plus h minus f of x divided by x2 minus x1. You can just see nothing but this is giving a slope. It's always going to be a slope. If y equal to f of x represents a curve, then the derivative will always represent slope of a tangent. Tangent word I've used. How, sir? You could have only said slope of a line, but you're using the word tangent. Listen carefully. As I said, from here, point P I'm fixing. And now I want to walk over this curve y equal to f of x. Okay, from the point Q. So I'm here. Now see, if I'm here, I'm gonna take this color. I'll use some other color for yes, I'll come with some more colors so that the things will be very clear. See carefully. When I'm here, for example, walking now here, if this point is Q now, the new Q dash will say, now join this. When I join, you see the secant this has reduced a bit. Again I walk, and I come here. When I come very near to P, that's why you're saying h is tending to 0. When this distance is 0, or as in how I am here, my corresponding value on the curve is here. Again I'm here, corresponding value is here. So ultimately what's going to happen, that both of this, let I just show you the mic, zoom level of this. See, it is like this, the curve is like this. I'll do one thing, I will redo it here. Better, I will redo it here. This is far better to visualize. Same thing, I will take it here. No change. Only I thought, it's very small here. See carefully. x here. Corresponding value is f of x here. Again, x plus h. Then the corresponding value is f of x plus h. Okay. Now what I'm saying is this point P, x value is x itself, y value is f of x. Let us write this properly. F of x. So this coordinate will be f of x. I repeat, the coordinate of point P will be x comma f of x. Then for here Q, my x value is x plus h and my y value is f of x plus h. Okay. Now when I want to join the point P and Q, see carefully, point P which is here. So join this, we get a chord, or we can also think of secant. I'm extending. Okay. Now I'm going to fix either P or Q and I'm going to walk over the curve y equal to f of x. Now I'm going to walk over same graph I've just went in the zoom level. Okay, now you see carefully. As this distance, I have said, is h very small. So as I'm going to come here, so the curve I'm here. Now see, when I'm here, let's say Q dash or Q1. Now see, from here, this will be my new chord or secant. Now, as and how I move, because h is tending toward 0. As and I'm going to move, ultimately one day will come that when I'm walking over the curve here, I will be here. As soon I'm here, as soon I'm there, you see, we are going to have a tangent. A tangent we are going to have. That's what I'm saying. The first derivative represents slope of a tangent. Okay. If y equal to f of x represents a curve. Now the question is some basic level question. Okay, and the tangent need not be parallel to x-axis. I have made sure. Okay, it may not be. Okay, that's what I'm saying. Now, one question comes is, now this we understood, and this we call first principle. This we call derivative by using what? First principle. And first PUC by using this itself, we have went for derivation of sine, cos, all that. Now having understood this, and here plus 6 minus is getting cancelled. So ultimately you will get this one as what? Limit f of x plus h minus f of x divided by h, where h is tending to 0, dy by dx. Okay. Now let us have some basic thing there. From school days, at a point on a curve, how many tangents can be drawn? As you can see, only one tangent. This tangent was there, no? This line. Okay. So at a point, only one tangent is possible. Now the question is, no, when we say non-differentiable, what's the meaning? It means at that particular point, we are not having a unique tangent. For example, see carefully. If I think of y is equal to mod of sine x. See carefully here. Here, when I draw the sine, see, sine s graph is this one, right? But mod is there. Mod will convert negative to positive. So upper part of the graph no change, but this below part is there, no, it will not sweep, just it will move up. Okay, so it is going to be this. In place of going down, again up, again up. Here also same. Now see carefully. At the point here 0 it is, here pi, here 2 pi, here minus pi. At pi, you see how many tangents are able we can draw. See carefully. We can have one tangent here and one more here. Similarly, you see here also. This see here also. At the beginning, when I discussed modulus function, I used the one word kink, sharp bend. You can see a sharp bend. Before I've drawn the graph, means tangent. You see again I'm drawing it here. You can see a sharp bend here, kink, which we call what? Kink. So When we say it's not differentiable, meaning is at that particular point we can have more than one tangent, but from school days we know we should have only one tangent at a given point. So whenever we have more than one what tangent at a given point, only then we say it is not differentiable. Similar, now coming to the some conclusion part. Okay, first you make a note of this, then we will go ahead, make a note. Now, under what all condition the function is differentiable, non-differentiable, let us have one result and then we can go ahead with the problems. One marker problems. All one marker problems are on continuity as well as on differentiability. See carefully. A function is differentiable. For example, you see this curve, it's a smooth curve, then the function is always continuous also. So differentiability, if a function is differentiable, implies continuity. As it is continuous, limit exists. All in one line I'm giving. Next, if a function is continuous, then two things can happen. It may happen that it is non-differentiable. Any example, sir? Yes, it's here. Or it can be differentiable. So both the things can happen. Then what to do? You have to check for this case. You have to check for this case. You cannot comment directly the way we can comment here. Next, this is continuous. Next, what about if the limit exists? Okay. Before that, discontinuous. As soon a function is discontinuous, it also implies that it is non-differentiable. As soon you know it is not continuous, you can also say it is non-differentiable. Okay. Fourth point, if limit exists, it may be continuous or discontinuous. You have to check. You have to check this. You cannot comment anything directly. Okay. So with this logic, we can go ahead for one marker question. Yeah. Okay, dear students, I thought before I just start with the problem, let I just give the expression for differentiability, non-differentiability. Okay, I mean to say left-hand derivative, right-hand derivative, and also left-hand limit, right-hand limit. Who knows, for assertion reason type one marker question, that will be useful. So first, coming to continuity, see carefully. Coming to left hand limit, in place of writing like this, we can also write this one as f of, see carefully, what's the logic here? X is here, A is here. I am moving towards what? A. So very clearly from the number line, I am coming left of A, therefore it is left hand limit, and X is less than A. When X is less than A, if I transpose A the other side, X minus A is less than 0. And this difference I have taken as H. So H is negative. So in place of X minus A, I have taken H, and H is negative. So solve for X. What you will get for X from here? A plus H. So in place of X, A plus H, where H is tending to 0 minus. So this minus is saying that I am coming left of 0. The other way of writing this can be replace H as minus H here. So I will have limit of f of A minus H as H is tending to 0. Why this minus is given? Because now when we say H, no, we have a habit, no. What is H, positive or negative? We'll say positive. Why? We'll see plus sign here. But H is what? Actually negative. So while evaluating, student will get confusion. So in place of that, let that minus be visible for the eyes. Okay. So left hand limit is f of A minus H as H is tending to 0. Similarly, right hand limit. limit of f of x as x tends to a plus is what? Limit of f of a plus h, but this time h is tending to 0 plus. What's the logic, sir? Very simple. X is here, a is here. No, this time a is here, x. I am coming from right of a, and from the number line it's very clear that a is less than x, or I can say x is more than a. Simple, no? If 1 is less than 2, this implies 2 is more than 1. Transpose the other side. X minus a is more than 0. X minus a is h. Again the same. Now this time it is positive. So that's what I said, no? And you can see here, what is this? X minus a, it is h. So x is equal to a plus h. Okay. So here also you see a plus h was there, but h is tending to 0 minus, but here it is 0 plus. And here this will be your right hand limit and this will be your left hand limit. Okay. So who knows, for 1 mark, they may ask you the expression for left hand limit, right hand limit. Okay. Now here itself, let I give you on differentiability also. Now coming to differentiability, left hand derivative, nothing but the same point here. I'm applying from the left. So in place of now left hand limit, since I'm finding the derivative, left hand derivative, and we are going to go with the first principle concept only. So it is going to be limit of f of a minus h minus f of a divided by h as h is tending to 0. Okay, other way of writing will be, or limit of h is tending to 0 minus f of a plus h minus f of a divided by h. This is the primary definition. Again, if I replace h by minus h, I'm going to get the above one, and with one minus sign here also. Okay, now coming to right hand derivative, limit of f of a plus h minus f of a divided by h as h is tending to 0 plus. So if at all we say a function is differentiable, left hand derivative should exist, right hand derivative should exist, and both should be equal. So left hand derivative should be equal to right hand derivative, and that we denote by f dash of a, nothing but that it is differentiable at the point a. So having this, but in our computation we're not going to use this, but I just thought for a search and result type question, if they ask, you should know the expression. Kindly make a note of this. Yes, dear students, we are ready for 1 marker question from all the 3 model papers. I have made sure I have just kept as it is. It will be helpful for us, no, to get the answer quickly. Model question paper number 1, as we know, this is issued by KSEAB, and for this academic year 2025-2026. Question says, model question paper number 1, choose the statement that is not true from the options given below. I want incorrect answer. For this reason only I spend the time on detailed concept, and no doubt, as I've said, after we complete this, our target is KSEAB for definitely, and there, no, these are my basic videos. Okay, so option A, every polynomial function is continuous. We all discussed every polynomial function is continuous. This is true, but they want in not true. So option A out. Every rational function is continuous. Yes, it's continuous in its domain. True. So this is also out. Every differentiable function is continuous. Differentiability implies continuity. Yes, this is also true. Next, every continuous function differentiable. Coming to continuous function, it need not be differentiable. It may or may not. We should always check. So here they have said it is continuous. Here they have said every continuous function is differentiable, and this is a false statement. So option D is the incorrect one. Okay, I hope this is clear. Now come to this. The function f of x is equal to rectangle bracket x, where they are saying rectangle bracket stand for greatest integer function is. Before we talk about that, recall the graph of greatest integer function. The graph of greatest integer function. See carefully. The graph of greatest integer function. So from 0 to this, open at 1, then this is 1, 2, minus 1, minus 2, and here 2, then again open. Then between 2 to 3, between 2 to 3 it is 2, and here, and again, yes. Now let us try to see this. First, discontinuous only for integral. Yes, you see, when I just take my hands only at integral points, so option A is actually correct. But let us also try to understand the remaining option for better understanding. Constant function, no, it is not constant. In a particular interval, for that interval it's constant, but for throughout R it is not constant. You can see the graph is changing. So option B is out. Continuous, nowhere. Derivable for all x, it's not derivable, nothing but differentiable. It's not differentiable. Reason, it is discontinuous. Whenever a function is discontinuous, it's also not differentiable. So this is also out. So only option A is correct for this. Yeah, make a note. Yes, dear students, we are with the last problem on differentiability. Again, I repeat, we are going to have part 2 on only methods on differentiation. Okay. Now see, the derivative of, is it recording? Yeah, the derivative of f of x equal to mod of x minus 3 at x equal to 3 is, we call mod x graph. Okay, so here f of x is equal to mod of x minus 3. Already I discussed that. Whenever we have mod, the term inside the mod equate to 0 to get the graph. So x is equal to 3. When I talk about x equal to 3, see carefully. At x equal to 3, I will have a V-shaped graph. And if you see very carefully, here you have got a kink, nothing but sharp bend. Kink means sharp bend. And at the sharp bend, the function is not differentiable. For this case, we can explain like this. As I said, if y equal to f of x represents a curve, the first derivative stands for slope of the tangent. At each point, we can have only one tangent. Correct? No? Here I can say every line is tangent to itself. And at point 3, we have got two tangent. One is this, other is this. This equation will be y equal to plus of x minus 3, and this equation will be y equal to minus of x minus 3. Okay, this is minus, mind it. Okay, so it is not differentiable. So they ask derivative, nothing but differentiable. It's not. So option D will be correct, not existing. Okay, I just thought that one expression I'll give you on derivative with this, the problem is completed. See, when we say y equal to f of x is given, then when I differentiate the first principle dy by dx, let it be, or f dash of a, let it be, this is given as limit of f of a plus h minus f of a divided by h, as h tends to 0, if it is differentiable at a point a. Okay, so this will be at x is equal to a, that's the meaning. But it is in general, then I'll have this. So let you know, who knows, for 1 marker you may have a question on this. Okay, yes, and even this basic graph y equal to mod x. See carefully, what will be the graph of this? Let us try to take this problem here. So what will be the graph of this? Y equal to mod x. This is the graph. This is y and this is x. So we have a kink. Where do we have a kink? For y equal to mod x, the term inside the mod equal to 0. So here we have a sharp bend. So we have a kink. Therefore, it is not differentiable at x is equal to 0, even though it is continuous. So x equal to 0 is point of non-differentiable. X equal to 0 is a point of non-differentiable. Okay, yes, dear students, totally 5 marks. From this we have covered, that is, one is 4 marker, other is 1 plus 1 marker, and from all the model paper we have got a problem on continuity and differentiability. So continuity and differentiability. So I thought, why not to take one entire video on this. It will be anyway going to be helpful for CET as well, and as well as the higher other entrance examination. So with this, we come to end on this part 1, which is only confined to continuity and how we are going to check whether it's differentiable or not. And this will be very important for us. Make sure be thorough with this. Okay. So with this, we come to an end. Study well, hard work, be dedicated. Okay. All the very best. Study well. God bless you all. And do share, like, and subscribe to my YouTube channel, Math Universe with Dr. Naseer Ahmed. Thank you all.